cylinder object. So, for example, when you have a map from A to X, suppose you have such a diagram. So this is inclusion 0, inclusion 1. The cylinder object and the map H with a homotopy, which factors two maps F and G. So this is left homotopy and right homotopy is done through the path object. So there is A from yes. A goes to X, X goes to Xi, yes, yes, and Xi goes to well, actually it goes to this, but we can by universal property induce these maps. So these are two homotopies which we're interested in. So there's homotopy through cylinder object and the homotopy through path object. Wait, which is the homotopy? The homotopy is between A to the I. Wait, from A to X to the I. So the homotopies are these maps. Okay. So now let's discuss how they are related between each other. So theorem. Suppose F and G are maps from A to X. Then if A is cofibrant, then left homotopic is also right homotopic. And if X is fibrant, then the other way around. So these two claims are obviously dual. So let's discuss only the first part of the claim. Okay. So let's start our proof by choosing the good left homotopy, such that the cylinder object is good. This thing is F, this thing is G, and this is a homotopy. Okay, we have this diagram. Now let's try to find this map H, H prime, let's say. That will give us the right homotopy between these two maps. Okay, so as A is cofibrant, we know that if A is cofibrant, then this inclusion called A0 is actually an acyclic cofibration. So this one is actually an acyclic cofibration. So we draw this diagram. Here we need to have this is x to the x, and this is xi. X. This here is path object. So okay, let's. So what is this map? This map is A0. It's an acyclic cofibration. This map is also known. It is this map. It is just a fibration. What is this map? This is the product of two maps. The first one is just this from the definition of path object, of the good path object. Yes, so we take this as a good path object. Yes. Okay, so here it is a fibration. What is this map? It is a product of two maps. One map is just H, and the second map is let me try to remember. It is so we have this map. Let's say this is I and this is J, and we have also this map. Here, this is just F. So this map is just Fj. And what is this map? This map is is actually a composition of two maps. One is A to AI. No, wait. Oh, wait. This is not here, but this is F. Let me try to remember. This is the map FQ. QF. So this map, let's here this is let's see this as a good path object. This is a good path object. So this is this, and let's name these maps P and Q. Okay, so here is the map F to X, and this is the map Q from X to Xi. Wait, doesn't really matter. Q and P. So this is just our map F, and this is the map from the diagram of our good path object. Okay, so let's see that indeed this is a commutative diagram. What is this map? It is inclusion as the lower as a lower part of the cylinder, inclusion as a lower part of the cylinder, and the first one is Fj, so J is just here, so this is just ID, and if we compose it with that, this is just F on the first part, and the second part is Hi0. And Hi0 is also F. So this is a map F times F from these two maps. And what is this map? This is F, and this map is just two copies of ID. So this is also F times F. Okay. This is indeed a commutative diagram, so, and this is an acyclic cofibration, this is a fibration, so we have a lift. Let's call it K. So we have a map from A, I'm sorry.
Can you repeat this?
We want to show that this diagram is commutative. So the composition of these two maps is just F times F, because this is F, because this is just inclusion and composition with F, and this is Hi0, which is also F by homotopy. And this is just map from, this is just F, and the composition of these two maps is just ID times ID. So this is also F times F. So this is commutative. So we can use the fourth axiom to and we have a lift from this to this, from the cylinder object to the path object. Okay. So what we need from this, from this lift is just that Kp, Pk, is equal to Fj times H. So what is this is what we'll need. So okay, let's try to build our homotopy. So our homotopy is actually okay. Let's try to build X Fg path object and two maps. Oh, no, not a, yes, Fg. This is not good. I don't like this picture. Okay. So we have these maps, F and G. We need to wait. I'm a bit confused. So the argument is that the map from A to Xi is given by Ki1. So we have I1, K. Okay, so we have this diagram.
Yes, but this cylinder object is not X. In the definition of right homotopy, you should place X.
Yes, you are right. So this is why I was a bit confused.
Okay.
So
No, I think you have a lift K. It's arrow from cylinder object to X. I think you should.
from cylinder object to
Yeah.
X.
From cylinder object to
No, we want to have a right homotopy, so we need a map from the path object to X.
okay,
Okay. So no, wait, no, not from path object to X, but from A to path object. Yes, I'm sorry. So yes. So there is. So there are these two maps, which are right. Okay, let's try to improvise a bit. So what is KI1? KI1. Let's first let's see this composition. KI1 composition with this map xi to x times x. It is called P. So this composition is just so we know that pk equals to fj times h. So
yeah, I think you have projection from x times x to x.
yes.
Push out property of
Uh,
x times x.
So you want to
Yeah, I think it sells, but I don't understand why I have.
no. If we have a push out, but we have this.
Yeah, why we have these two arrows?
Because there is a map from to the. We have a map. These two maps are just compositions.
Okay.
Yes.
Yes,
Okay, these two maps are just compositions,
Yes.
and Ka1 is it's okay. Let's see what is the composition of from Ka1 to composition with this map.
Yes.
So.
Maybe this is G and F. That's okay.
Yes, they must be G and F. Let's see that. So pKa1. What is pKa1? So we know that pk is equal to the product of these two maps, fj and h. So it is fj I1 times hi1. So fji1, ji1 is just an identity, as I remember. Yes, this is just an identity because of this map factors. So this is just f. And what is this? This is by homotopy the map G, h, I1. So we get what we needed. We got a map that gives us homotopy between f and g. Okay. So if we know that, we know that if both A and X are cofibrant, we will call if A is cofibrant and X is fibrant. We will call this relation left homotopy, right homotopy, just homotopy, because it is one-to-one. So definition: if A cofibrant this will be called just homotopy. Okay, and
Sorry, I didn't understand one moment.
okay,
In the right, in the left word, you have a definition of right homotopy. And
yes.
I see two arrows from A to X.
Yes, these two arrows. Maybe I don't need them. Let me see.
Why we didn't use two arrows and we didn't construct these two arrows?
Because they're just F and G.
Yes, these two arrows is F and G.
Yes.
Okay. And sorry, what about the main
Wait.
part of this definition?
Wait, maybe we don't need them actually. We don't have them here because, yeah, maybe we don't need them.
And okay.
Yes, you're right. We don't need them in the definition of right homotopy, and this is.
We need only arrows from A to X and Y.
No, path object. Yeah. Yes. Okay, so we know what is left homotopy and right homotopy, and we know just what is just a homotopy. So, let's. Okay. Okay. Let's now prove our regular definition of homotopy that we know from topological spaces. So for first definition, suppose F and G are maps from first to from A to X and from X to A. So F from A to X and G from X to A. We say that they are homotopy inverses of each other if Fg is homotopy equivalent to ID of X and GF is homotopy equivalent to ID of A. So this is just a regular definition from regular definition of homotopy in topology. And the theorem says that these two definitions actually coincide. That if suppose so if F and G are homotopy inverse maps. Oh wait. No. If F has a homotopy inverse, then F is a weak equivalence. And vice versa. If F is a weak equivalence, then F has a homotopy inverse. Okay, let's prove it. Suppose we have a map from A to X. No, wait. I forgot some. Conditions, and this works if A and X are both cofibrant. F from A to X. A and X both fibrant and cofibrant. So if A and X are nice spaces, then we have the homotopy, we have the analog of homotopy definition for topological spaces. Okay, so if we have a map from A to X, we can, by the last axiom, split it. We can make it as a composition of two maps. A composition of, for example, a cyclic cofibration and a fibration. So let's call them I and J, Q and P. Okay. So let's note that if we know that A and X are both fibrant and cofibrant, then C is also both fibrant and cofibrant because it is a composition of, for example, here it is a composition of two cofibrations, or and the composition of two fibrations.
One question.
Yes.
F is weak equivalence that includes that then A and X both fibrant and cofibrant.
No, this is the condition. So this is the condition for this to work. So this is the first. Actually, it must be on the first it must be above all of this. This is the condition, and this is these are the statement of the theorem. The theorem.
This is self-weakest complexest state.
I don't understand what they said.
My theorem works in self-weakest, I think. Let's see.
Ah. Okay, maybe.
Okay, sorry.
It's all right. Okay. So we know that C is both fibrant and cofibrant, and we know that. So the first prove the second part of the theorem. If F has a weak equivalence, and then it has a homotopy inverse. So how would we do that? We know that this composition is F, and this is a weak equivalence. So by the 2 out of 3 property, we know that P is also a weak equivalence. Okay, and now let's. So what's the plan? We need to show that it has some form of a splitting. We need to show that there is a map R such that the composition is ID. So how would we do that? Okay, so we have this map A, C, X. We have this diagram. So these are two Q's, this is P, and this is also P. No, that's not good. That's not good. Wait. No, we don't need that. We need from C to A. We need this. We need this. We need. I need to check my notes. Okay. This was almost what we needed. So we have this diagram. We have this diagram. This is an initial object. This is a composition of two cofibration. So it is a cofibration, and this is an acyclic vibration. So there is a lift. Let's call it. I don't know. Yes, let's call it R. So what it actually does? It is actually mapped from C to A, such that QR is equal to IDA. RQ is equal to IDA. Why is that? Because these are two identical maps, and this map is ID. Okay, so we have this map. And by the same argument, we have a map from X to C. Let's call it PQRS, which splits this part of the diagram. So the claim is that the map SR actually is the homotopy inverse. So how would we do that? We can actually check that R is a homotopy inverse to Q. Well, RQ is equal to IDA, so
what's homotopy inverse?
Homotopy inverse, it's here.
Homotopic. is cofibrillant and X is fibrillant.
Yes.
And so if we take FG, this will be a map from X to X, and
All the objects are both fibrant and cofibrant here in this setting. So
okay, so this definition only makes sense for objects which are both fibrant and cofibrant.
yes, and this is why I forgot at first, but this is the condition for the theorem to work. Okay. So in the on one side it is easy because RQ is just equal to IDA. We don't need to have a homotopy here. But let's see what's on the other side. So we need to check that QR is homotopic to IDX. Okay, let's check that. And I have to check my notes. So QR is no, it's IDC. We were both wrong actually, because it's first R then Q. Yes.
Okay.
So it's IDC. Yes. So what's the diagram we need here? So let's draw this diagram. So there is a map from X, right? No, we don't need to have diagram here. It is easier actually. We know that Q is an acyclic cofibration. So by the theorem we proved a week later, it induces
Last week.
yes, last week. It induces a bijection on classes of left homotopy maps by precomposing. So Q star from left homotopy, right homotopy. I suppose left homotopy. No, it's from right homotopy. From right homotopic maps from right C to C, I suppose, to right homotopy maps from A to C. Yes. Yes. I see. Okay. This is one-to-one. So let's see how this acts on RQ. RQ? No, on QR. QR is ID. We need to check that QR is equivalent to IDC, homotopy equivalent to IDC. So this is just equal to QRQ by precomposing. We know that this is equal to IDA, so this is just Q. But we know that this is one-to-one, and we know that Q star from IDA is also equal to Q. So these are right homotopic maps. And we know that if in our setting, right homotopy means just homotopy. So okay, we prove it in one direction, namely if if f is a weak equivalence, then it has a homotopy inverse. Let's prove it in the other direction.
So yeah, the right inquiry from right homotopy C.
Yes. So we proved that R is is a homotopy inverse to Q, and analogously we can prove that S is homotopy inverse to P. So the composition is homotopy inverse to the composition.
Yes. My question about it. Why we have this arrow Q star? It's composition with
So this is about this line, yes? The question is about this line, yes?
yeah. What is Q star?
Q star,
Composition with Q.
yes, this is pre-composing with Q.
Okay.
Yes.
Yeah.
Okay, so let's prove it in the other direction. Mhm. Okay, so we have two maps which are left homotopic, and we need to prove that it is a weak equivalence. So let's let's start from the same picture. So we can represent F as a composition of two maps which are which is an acyclic covibration and just a vibration. F, Q, P. Okay. So if we prove that P is a weak equivalence, then by 2 out of 3 we say that F is also a weak equivalence, and we are done. Okay. So let's first show what does it mean that Fg so G is a homotopy inverse. Let's see what does it mean that Fg is homotopy equivalent to ADX. So there is two maps from X to X. This is just ID, and this is a map. This is G, and this can be decomposed as two maps, C, Q, and this is P. Okay, so let's say that we have a left homotopy. So it is a map into a coproduct, then the map into the cylinder object, and this. This is a homotopy. This is inclusion 0, inclusion 1. We need to have a diagram. So the main trick we use is just have some commutative diagram and a lift. So let's see the lift. So a diagram like this: x, x, see. Okay. X, A, C, X, and X to the I. Okay, let's now see that this is G, Q, P. This is I 0 and H. So this is just this triangle. So this computes x to the xi because x is cofibrant. This is an acyclic cofibration. So we have a lift. Let's call it H prime from X to this T. Okay. So my claim is that H prime I1 from X to the C is a splitting, yes? No. Let's call H prime I1 for convenience. Let's call it S. So this is a map from X to C. So what we need from this diagram that PH prime equals to H. No. Yes. So from this we can see that PH prime I1, this is just PS, and what is this? What does it equal to? H prime I1 is IDX, so it is just P. Okay, so we know that PS equal to P is equal to P. So so wait, PS, no, wait, that's not good, because PS is a map from X to X. No, yes, I was wrong here because P H prime equals to H, P H prime I1, so it must be, so it is equal of course to PS, but P H prime I1 is equal to H I1, and this is equal to IDX. So we know that IDX is equal to PS. Okay. Okay, so let's use what we proved on the rightmost board. We know that Q is a weak equivalence. So by this theorem, it must have a homotopy inverse. Let's call it R from C to A. Inverse to Q. And now we have some actually purely algebraic task. we know that SP we know that SP is equivalent to SPQR, yes? SPQR, because or SPRQ. Wait, SP is a map from, yes, SP is a map from C to, да, Сената граждан Рима. Так, so SP is a map from X, wait, what? I'm a bit confused here because S is a map from Xi, from X to X. It is a map from X to C. Okay, it's all good. It's a map from C to C. Everything's all right. So QR is a map. R is a map from C to C also. So okay, everything's good. So this is equal to this. We know that PQ is equal to is just equal to F. Yes. Wait. No. Well, maybe that's true, but we don't need this. Okay. SP is equal to QGP. Why is that? S is equivalent to QG. Yes, wait. So the claim is that SP is equivalent to QGP. Yes? Yes, that's what is written here. Why is that? Because S must be equivalent to QG. So QG is a map from X to C, and S is a map from A to C. And what is the homotopy between them? Let's see it. So there is a map QG. There is a map S, I1H, say C, yes, and let's try to build a left homotopy between them. So this is H, this is I1, this is Q, so H prime. Yes. So the claim is that H prime gives a homotopy between S and QG. Yes. Between S and QG. So this wait, xi. So this part of the commutative diagram commutes because this is just the same diagram essentially, and this part of the diagram commutes because it is this part of the diagram. This is because this is this triangle. So we have that S is left homotopic to QG. Okay. And this is homotopic to QG of R, and why is that? So let's write it first. Why P is homotopic to FR? Well, because yes, because this R is homotopy inverse, and because this R is homotopy inverse, we can QG. Okay, let's. So P, we can, if we have P, we can write here QR in the right order, because this is homotopy inverse, so it is equivalent to homotopy equivalent to ID, and PQ is equal to F. It is just equal. So QGFR. Okay, and the GF is equal to GF is homotopy equivalent to ID, so it is just QR, and QR is ID. ID A, I suppose. Yes. Oh wait. No, it's ADC. It's first R, then Q, and SP, and also SP. Firstly P, then S. So we have a homotopy inverse to P. Yes. Yes. So so SP is homotopy equivalent to the ID. So it is a weak equivalence. There was a theorem that maybe I forgot to say that the maps homotopic to ID are just weak equivalences and only them. So SP is a weak equivalence. So the only thing we need to prove is that P is a weak equivalence here, and it is true because P is a retract of SP by this diagram. So C SP P. This is wait, not SP, here X, C to X here, and here we have also from C to X P. Yes, must be true. So this is just composition, and this is just by this, because PS equal to IDX. Okay, we have this composition. So P is a retract of SP. So SP is a weak equivalence. So P is also a weak equivalence. So by 2 out of 3, F is also weak equivalence, and we finally proved our theorem. Okay, and maybe for the last 5 minutes or so.
Well, you still have at least 10.
At least 10. Okay, I will try to to give a definition, maybe skipping some proofs of homotopy category.
Well, there are the homotopy category is the same as the category localized at quasi or at weak equivalences.
Yes.
So the theorem which we're ready to prove is that the homotopy category of a model category is equivalent to the category of fibrant and cofibrant objects with homotopy equivalence classes of morphisms as morphisms. So let's just state the theorem, and basically I think we're more or less we have all ingredients which are needed to prove it.
So okay, maybe I will give a definition, give a functor from homotopy category, from category to the homotopy, from the model category to the homotopy category of it. So first, every object has its cofibrant representation. What is it called?
Replacement.
Cofibrant replacement and fibrant replacement. So there is a map from initial object to the object. So by the last axiom, we can decompose it into cofibration and acyclic fibration, and the map QX is acyclic, is cofibrant, and this is equivalent, so it is called cofibrant replacement.
And similarly,
Yes.
every object has a fibrant replacement.
Yes, X point. Also this, oh no, this, fibrant replacement.
And in general, those QX and RX are not functorial in X. It doesn't follow from the axioms of a model category that QX, for example, can be chosen to depend functorially on X. However, in most cases which occur in everyday life, both the fibrant and cofibrant replacement can be chosen to be functorial in X, and both factorizations of morphisms can also be chosen functorially. Basically, we will not prove this, but it's something which is useful to keep in mind.
Yes. So the statement is that if we have a map from X to Y, there is also a map from cofibrant replacement to a map between cofibrant replacements. F and F prime, and also for the fibrant replacement, also we have we also can have a map. So we can call it a functor gamma. So there is a functor gamma from. Okay. So suppose we can. So what is homotopy category? So homotopy category. So objects of this category are just objects are just objects of the initial category. And so the interesting thing, what are the morphisms between two objects from X to Y? Okay, let's say that this is a functor Q. This can be viewed as a functor, and this is a factor R. And also, let's say that there is a functor R prime from the subcategory of I need to remember, from the subcategory of fibrant or cofibrant, from the subcategory of cofibrant object, I suppose. Yes. To the yes.
Почему это функтор? Значит, Rx это не функтор, это какая-то фибральная замена. В общем случае она не функториальна.
Okay.
So the Rx in general for general model categories is not functorial, so it can be chosen for every x in some way, and in most cases this Rx can be chosen to be a functor, but not in general. Also, the homotopy category is C localized at quasi-isomorphism or weak equivalences.
Yes.
So this is the definition. Now, if C is a model category, then there is a way to calculate the morphisms as the homotopy classes of morphisms in C between Qx and Ry.
Okay. So in this paper, it's the other way around. Actually, the
Yes,
definition is.
Well, it's a question of philosophy.
Yes.
Normally, the definition should be a definition should be straightforward, and then there is a computational recipe or several recipes which can get convoluted. So basically, I suggest it makes sense to take the localization as the definition, and then the other version as a recipe to compute the morphisms.
Okay. So okay, let's say that it is prime, and this is just. Okay. So and the thing that I didn't say that this functors, not actually functors, behave good with homotopies. For example, if something, okay, if both x and y are fibrant and cofibrant, then f prime depends only on the left homotopy class of f. All right, homotopy class, I don't remember. So yes, if both fibrant and cofibrant, then just on homotopy class. Okay, so we say that there is a functor from the this is a full subcategory of cofibrant objects, and this is the subcategory of both fibrant and cofibrant objects with functors being
Why do you say it's a functor?
Because I don't know why it is called a functor here, but in the paper it is called a functor. This is the only thing I didn't understand fully from the paper, because I don't know why it is a functor.
Okay, and what is pi?
pi means that the functors are homotopy classes of maps. No functors. Morphisms are homotopy classes of morphisms.
Well, yes. In this case, it's a functor. If we take the homotopy classes of maps as morphisms and not just maps, and then we can choose the R functorial.
Okay. Okay, so let me finish the alternative definition. So this is R prime Q of x, y. R prime Q of x, C of this R prime Q of y. So we make, firstly we make a good both fibered and co-fibered objects out of x and y, and then we
Then we also need to question with the
yeah, so it's spicy, yes.
Does anyone understand what's going on? Значит, понял ли кто-нибудь хотя бы что-нибудь? Сейчас произошло что-то, что может пригодиться, что-то полезное. Значит, понял ли кто-нибудь хоть что-нибудь или никто не понял ничего?
Нормально все.
Значит, сам говорит, что нормально, Андрей. Так, значит, есть люди, которые следили, но не понимают все равно, что произошло.
А что, в смысле вы говорите, может пригодиться? Что вот конкретно?
В жизни вашей, в
Не,
статической жизни может пригодиться.
А важно, что из этого важно?
Значит, есть, значит, давайте поговорим еще раз. Значит, морфизм, если у нас категория локализация если у нас на категории есть модельная структура, то морфизмы в локализованной категории по слабым ковалентностям это то же самое, что значит, морфизмы из кофибрантной замены сорса, фибрантную замену таргета, профакторизованной по левой гомотопии или эквивалентно по правой гомотопии. Значит, если эти два соотношения совпадают. Значит, два респалинских это не доказывают, потому что это немножко более общее утверждение. Значит, два респалинских говорят, давайте мы эти сорсы таргет заменим на что-то, что будет и фибрантным, и кофибрантным. Но это не обязательно. Можно сорс заменить на фибрантный, таргет на кофибрантный, уже будет все хорошо.
Не наоборот?
Сорс на
кофибрантный.
Да, сорс на кофибрантный.
Таргет на фибрантный. Вот. И, значит, и потом, значит, левая или правая гомотопия совпадают, значит, даже по двум причинам, и, значит, мы там факторизуем по любой из них, получаем нечто.
Короче,
Вот это нечто, которое мы получаем, оно будет, значит, морфизмом не в локализованной категории. Это очень удобно. Вообще говоря, когда мы локализуем, у нас, значит, морфизм это неизвестно что. А вот если мы локализуем модельную категорию по слабым эквивалентностям, то есть вот такое вот явное описание морфизма.
Ну, понятно. В смысле локализация. Ну, короче, ничего кроме мотопических категорий не существует.
Ну, совсем нет. Это никто не говорил, это вы сами же говорили.
Ну ладно.
Okay, so summarizing, if we localize a model category in weak equivalences, then the morphisms are relatively straightforward to describe. We need to, well, suppose we have two objects, x and y. We take a cofibrant resolution of x and a fibrant resolution of y. And then we take C from the former to the latter. then we take the C from the former to the latter, meaning we move this C from the former to the latter, and we quotient by the homotype remain. And since the source is now coefficient times the target is different, it doesn't matter whether we take the right homotype or the left homotype. And this is a useful theorem which you may need to use in your mathematical life. You don't need to be doing category theory to appreciate the usefulness of this. Okay, well, Alexei, yes, so
Something like that.
what is W?
Says I don't know.
No,
but no, then yes, you're right.
We
Wait,
take
hold
the homotype. And this is the morphisms from X to Y in the homotype category, which we define to be C localized in C localized in W, where W is the class of the weak equivalences.
Yeah.
Okay, are there any questions? Well, then I suggest we have earned a break. We have earned a break. So let's have a break, and I think well, 20 minutes is a fair amount of time to allow us to recuperate, and then Mika will talk about transfer. Значит, давайте мы подумаем про субботу. Значит,
я, наверное, не побегу.
Ну, я тоже.
Ну вот. Okay, so we'll talk about right transfer model structure. In case when we have an adjunction and category C have model structure, is model, then we will define a model structure on category D as follows. Fibrations in D is are those morphisms that that are fibrations under action of U. And the same for weak equivalences. And cofibrations, and we will define cofibrations as morphisms that have left lifting property against weak fibrations that
a little bit of advertisement. Normally, checking the axioms of a model category by hand is difficult. So it's a good idea to have some sort of procedure which allows one to construct a model structure on some category, starting from a model structure on a simple category. There is one such procedure which is very useful, and it's called the right transfer. There is a similar procedure which is called the left transfer, and it's for some reasons less useful. There are other ways to get a model structure without directly checking the axioms, but let's start with this one.
Yeah. So these three classes are not always give us actual model structure.
We have declared the weak equivalences, fibrations, and cofibrations to do this, but there is no guarantee that these three classes will have all the properties which are contained in the axioms. We will check this.
Yeah. For example, there are two ways
how we can think about acyclic cofibrations. The first one is the cofibration is weak cofibration in this sense that it is cofibration. Okay. Cyclic. It is a cofibration that weak. That weak in this sense. And second, acyclic cofibration. We know that if we have a model structure, then cyclic cofibrations is exactly maps that have a left lifting property against all fibrations. We will call these maps
belong to weak equivalence.
We'll call those maps anodyne.
Anodyne, значит, незаметный. Inconspicuous.
Я видел перевод что-то типа успокаивающее, обезболивающее.
Усыпляющий.
Да.
Ну, значит, незаметный в смысле не бросающийся в глаза, не раздражающий.
Okay. So if we
Okay, so the left-lifting property against all vibrations, that's the second one, and the first one, left-lifting property against acyclic vibration. So once again, let's replace weak with acyclic. Does everyone understand the difference between 1 and 2?
Yeah.
No.
If this structure is actually a model structure, these two classes are equal.
But we don't know yet whether or not we do get a model structure.
Yeah, and definition, if these two classes give us a model structure, then it called right transit model structure. If they actually give us one.
Yes. In this construction, the functor F is a left adjoint, and the functor the functor U is a right adjoint.
Yes.
So when do we this gives us a function which is right adjoint because there's a left adjoint in the free form. Complexes are easy, algebras are complicated, and we want to have a model structure on algebras starting from a model structure on complexes, and this is where this construction comes in.
Yes. We will talk about it at the end of the talk. Okay. Theorem. Right transferred model structure exists. Exists if and only if these conditions are have a place. For every morphism in category D, we have factorizations of the form a cyclic fibration followed by cofibration and just a fibration followed by an anodyne map. And the second condition is that anodyne map is weak equivalence.
Weak equivalence is the key word in this expression is the word equivalence, not the word weak.
Okay.
Does everyone understand what it says on the board? If not, let's ask the speaker.
Okay. Clearly, these conditions are necessary because in model category we indeed have those factorizations. If we know that anodyne map is a weak equivalence, is a cyclic cofibration. Yeah, I need to say one thing before is that anodyne map is always cofibration because we defined cofibrations as maps that have left-Luthian property against acyclic fibrations, and anodyne maps as those maps that have left-Luthian property against all fibrations. So if map has LLP against all fibrations, that it has LP against acyclic fibrations.
Does everyone understand what LLP stands for?
Okay.
Sorry, but what is LP against all fibrations? Because in classic
say again?
I mean, we have a diagram, vibration, yeah, vibration and co-vibration. And we have FTP property against, I don't know, weak equivalence vibration or weak equivalence co-vibration. Yeah. Lifting property.
Yeah. In model category, we have lifting in those two types of diagrams. And we know, it's a statement that if a map has lifting if you have a map, say P, that have lifting property against for every.
Okay. Yeah. Understand.
Okay. So if you know that anodyne map is a cofibration and it is weak equivalence, then we have the factorization that we need in model structure. Fibrations that followed by a cyclic cofibration. So these conditions are necessary. Why they are sufficient?
Почему у нас все время 2-2?
Ну,
Все время 2-1 не было.
Хорошо. Пускай не будет номеров.
Сейчас ответ.
Okay. We must check all axioms of model category. First, all these classes of morphisms are closed under composition and retracts. This is clear. This is because if so if you have a retract of say F, retract G of F. And let F be a fibration in D. So we know that it is image of it is a preimage of vibration in C by functor U. So if we применим функтор U, we will see that U of G is a retract of U of F. So if U of F was a vibration or an acyclic vibration, then is U of G. And so by our definition of vibrations and cyclic vibrations, we also know that G is a vibration in D. And for cofibrations, we know that if map has left lifting property against something, then a retract of this map also have left lifting property against this something. I can talk about it.
Well, let's ask the audience. Does any of what's happening at the moment make any sense?
Sorry, I didn't understand what we want. G is a retractor.
At the moment, we're trying to prove that all classes of all these three classes of morphisms are closed under retracts. Now I showed that vibrations and acyclic vibrations are closed. It is on the board. And I state that cofibrations also closed under taking retracts, because if a map has left lifting property against something, that then a retract of this map has left lifting property against this something. Okay, I can just write it down. Assume that F is a cofibrations. F is a cofibration, and G is a retract of this cofibration. So we want to show that G has left lifting property against against all acyclic vibrations. So how would we
Sorry, but here is the name of the functor. Maybe the name,
Okay. Oh, understand.
X maybe.
Uh, we know that F has left lifting property against all acyclic vibrations. So we have a lifting of this diagram. I will erase it. Say, okay, it's not important. And I state that this composition is a lifting of map G in this diagram, because it is retread, so we know that
Yeah, the position of IQ is ID.
yeah. Okay, if it is clear, then we will continue. So we just proved that all classes are closed under retracts and composition. And
What exactly do we mean by all classes? The ones that we have on the left?
yeah, all three classes I will write. Now we will prove that anodyne map is a class of anodyne maps is exactly a class of cyclic cofibrations.
Whereby cyclic cofibrations, we mean the maps which are cofibrations according to this definition, and and also weak equivalences according to
Yeah, a cyclic cofibration in this sense, yes. So we know that anodyne maps are cofibrations, and by assumption we know that anodyne maps are weak equivalences, so we know an inclusion in this side. So we must show that every cyclic cofibration is anodyne, which means that every cyclic cofibration has LLP against all fibrations.
Okay, does everyone understand why we have this inclusion? Okay.
We will show that if F is a cyclic cofibration, then it is anodyne by statement that called retroact argument,
Which is useful on its own.
yeah, we will use it one more time in my talk. So we know that every map has a factorization of this type. Fibration followed by anodyne map.
Well, this is one of the assumptions.
Yeah. By assumption, we know that anodyne map is weak equivalence, and so is a cyclic cofibration. So by two out of three property, we know that I will call it P. It will be I, and it is F. That P is also weak equivalence. So we know that F being a cofibration has a left lifting property against P. We didn't know that if a map is a weak cofibration, then it has LLP against all fibrations. Cyclic cofibration. But we didn't know it yet. But what we actually know that all cofibrations has left lifting property against acyclic fibrations. So we showed that this fibration is acyclic. So F has left lifting property against this map.
By the way, we didn't prove 2 out of 3, but it's completely straightforward from the definition.
Yeah, I will write it down.
So 2 out of 3 for weak equivalences. Just by looking at the definition and remembering we do have 2 out of 3 in D, we get the same property for C.
Now with this all data, I will show that F is a retract of I. That is anodyne. So F being a retract of an anodyne map is anodyne itself, because anodyne map defined as a map that has LLP against something. So the retract of this also has. Why F is a retract of I? Firstly, I will draw a diagram of this form. That is commutative. P is a fibration, acyclic vibration, F is co-vibration. So we have a lift. Let's call it G. And so we can conclude that F is a redirect of I by looking at the diagram. Of this form. So GP is ID because of this triangle. And all is commutative. So we are done with this statement.
With which statement?
With this statement.
Yes, the statement is that the anodyne maps are precisely the acyclic vibrations.
Yes. So with this equality, we can we have the factorizations that we want. So this type of factorizations we
Well, basically, the first one is given by the first assumption, and the second one we deduce it from the fact that from the fact that we've just proved.
Yeah.
But basically, this statement gives us both factorizations.
Yeah, we'll write it down. Factorizations. And liftings.
Yes. Why do I have the liftings?
Yeah, because we again the first type of liftings, that is of this type, we had automatically by definition of cofibrations.
This is how we define the cofibration.
Yeah. And the second type we didn't know by definition, but now we see that this map is anodyne, so we have a lifting by definition of an anodyne map.
Which map is anodyne? The one on the left.
Yes.
Okay, so we know that acyclic vibrations are precisely the anodyne maps, and we define the anodyne maps as the maps which have the left-lifting property against all vibrations. So
Yeah. Okay, so we proved the theorem.
well, there is. Did we check everything?
Well, there is one axiom that that tells us that D is D has all finite limits and co-limits. I think we need to state this as a zero axiom.
Yes.
I think by the adjunction we have all limits if C has all finite limits. But what about co-limits? We can't say anything.
Well, okay, there might be a way to deduce this from the junction, but let's move on.
Okay. So now we have this theorem, this characterization, and we want some. We want to find some properties of category D that gives us these two conditions. Be true?
Do we need to assume that, D is the simple category. C is complicated. And we want to have a model structure of C from, want to get a model structure of C from a model structure of D. So here we need to assume that C has all limits and co-limits, don't we? Кто у нас буде, значит, у нас левый сопряженный, правый сопряженный, куда был левый сопряженный?
Левый сопряженный. У нас была такая картинка. Сейчас. Был левый, тут да.
So we want to have a model structure on C, starting from a model structure on D.
No, vice versa.
Oh yeah, sorry. Yes. So C. Okay. So C is the forgetful the right adjoint, which is in some applications the forgetful functor goes from D to C. So we have a model structure on C. We want to have a model structure on D. Okay.
So first we will talk about conditions that are sufficient to
So these conditions are not exactly user friendly. If we have an adjunction, it's not straightforward to check either of these. So we need some more. We need something more usable than what we have in this theorem.
Yes. Firstly, we will talk about existence of factorizations. So I will not state the theorem, but before the stating, I will give some definitions. First definition is a definition of cell complexes. Let I be a class of morphisms in some category C. Let's actually relative cell complexes. Let's call cell I, the class of relative cell complexes, the class of morphisms that obtained by transfinite compositions of push-outs of coproducts of elements in I. So it is the smallest class that closed under taking coproducts, push-outs, transfinite compositions, and contains the class I.
So, do you remember from yesterday what the transfinite composition means? Okay. Does this expression make any sense at all to the rest of the Что за зверь трансфинитная композиция? Понятно, значит непонятно, или лучше спросить докладчика?
I have another question. What's a coproduct of morphism?
So if we have two morphisms in I, say
So it's a morphism to the coproduct. It's morphism to
yeah, wait a second. Say I prime. Then I think it is just it is just a coproduct map from one coproduct to another.
Значит, зверь что такое трансфинитная композиция? Какой смысл вообще можно вложить в эти слова? Если какой есть?
Better I will I should talk about it. So what is transfinite composition? So transfinite composition definition assumes that C is has all co-limits. And assume that we have a diagram of this form where alpha is an ordinal. So it is порядочное множество.
It's a well-ordered set.
It's a well-ordered set, and as a category, it has an arrow between two.
Yes, so we can view ordinals as categories. Just draw an arrow from each element to the next element. Since an ordinal is well ordered, there is always the next element. There may not be a previous element, but there is always the next one.
Yes, so we can visualize this like this. And indeed, it looks like an transfinite sequence of an arrows.
If we have a function like x, we can view it as a possibly a transfinite family of x. Now, what's the composition?
Yeah. But we should say some something first that all image of alpha is okay, no. If beta is an element that has no previous element, it called limit element, I think. Okay, is limit? Well, it looks strange. Well, is has no previous element. Then the arrow from then x beta, that is element of this functor, image of beta by this functor is isomorphic to co-limit of an by n by all elements that are that less than beta. So in these limit points, we have co-limit of this scene that stands left. So then morphism from 0 element to the co-limit of this diagram. I may write just x. Okay. Is a transient composition.
What's this co-limit? Why do I have a co-limit here? Should we take the limit?
I think yes, because, for example, if we have CW complexes, we take a co-limit of n skeletons.
Но как у нас получается отображение co-limit? Сейчас x0 отображается каждый x гамма, правильно?
Да.
Хорошо. А почему отображение в копредел?
Нормально все кажется. Ну, в смысле же, как Миша же сказал, что мы хотим склеивать из островов клетки.
Да, но если есть отображение в каждый остров, то не обязательно есть отображение во всем. Чтобы отображение, значит, нужно...
Нет, если у нас есть отображение даже в нулевой остров, а нулевой остров вкладывается во все, то у нас есть отображение во все. То есть у нас есть отображение из каждого в копредел, значит у нас есть отображение из x0 в копредел.
Не, у тебя... Да, все нормально же. В смысле, все пошло.
But we need to include alpha in the coordinates.
No.
Okay, so we can take the co-limit непонятно все.
Ну, сейчас, у нас есть отображение из каждого элемента диаграммы в копредел. Ну, например, если у нас было там просто копроизведение, у нас есть отображение из А и из Б. Просто вложение. Ну, x0 у нас включается в этот.
Хорошо.
Нет, понятно? Ну да, у нас же есть отображение из каждого острова в Y, значит, есть отображение из всех. Вот. В смысле X. Все нормально, все работает.
У меня все вопрос про альфа. То вот, so if we, as it is written right now, we do not take the last element.
Well, I should just write x alpha, I think. Well, it is co-limit of those that left, but if alpha is not a limit ordinal, then we must write just x alpha.
Okay.
So it is what transient composition is. Okay. definition. Again, let I be a class of morphisms in C. Then we will call conf of I is a class of retracts of morphisms in cell I. So conf I is retracts of all relative cell complexes. Okay. Now we will talk about small object argument. This all the way to defining a cofibrantly generated model category. Definition: object X in C, some category C, is called K small for some for K being a cardinal number. Such that if we have if for every K filtered partially ordered set J, K filtered means that if we have a subdiagram of J that has a number of arrows less than K, then it has a co-column, which means that the element and the arrows that given us a commutative diagram. So, for example, for any pair of objects in our diagram, we have an element that and arrows that are that
That map into the cell.
yeah. So for every K filtered partially ordered set,
Especially to say capital filter.
okay, kappa. And a diagram of the form J in C, and for every morphism from X to co-limit of this diagram, we have a lift so have something like that. Что такое? У нас есть стрелки. So we have a diagram of the form J, f of J, and as our category is has all co-limits, we have a co-limit of this diagram. And we have a map from our object that should be k small to our to this co-limit. So object is called k small if this map has a lift. So if exists a map to какой-то элемент, to some element of this diagram that gives us a commutative triangle.
Okay, as everyone understands,
Or maybe I can give an example from topology. Or if we have a diagram of the form, say just an skeleton.
Let's give an example and a counterexample.
Okay. Let's take skeleton filtration of CW complex I, Y. So the co-limit of this diagram is Y, and let's take some topological space X and some morphism to Y. I state that if X is a compact topological space, then it is aleph 0, как это писать? Напишу просто так. And small.
Okay. On the other hand, if we take x equal y itself, then there is a map from y to y, the identity. But it doesn't factorize in general through any of the schemes.
Yeah, if y is infinite dimensional, then
Yes.
we have no.
Unless y is finite dimensional itself. Okay. So we I suggest we just continue. But other suggestions. Значит, Миша, сколько нам осталось?
Ну, нам осталось, на самом деле, сильно больше, чем я предполагал.
Так, значит, а сколько, вот если в пересчете на странице, значит, сколько мы сделали, сколько осталось? В пересчете на процент того, что ты уже сказал.
Я бы сказал 60%.
60%. Значит,
по-русски говоря, это еще час.
ну, я бы сказал, что это, значит, ну, с учетом оптимизма, это еще примерно столько же. Okay, so I suggest we're halfway through. Let's be honest with ourselves. We're halfway through, and I suggest we finish all this on Saturday in online on Zoom. And maybe Ashok will be able to speak as well, which will be good because his topic is also related to model categories. Another option would be to just have a break now and continue, but then we'll finish very late and everyone will get tired. So I think it's better to stop and continue on Saturday on Zoom. What do you think?
Честно говоря, у меня нет технических возможностей. То есть я не знаю, на чем я буду писать. Либо...
Я могу просто выложить.
Ага, хорошо, тогда...
Можешь писать в 306 аудитории под запись. Ну, в смысле, как, знаешь, как...
Интересно.
Если есть люди, которые могут, то есть умеют пользоваться вот этой штукой, то да, значит, на ней можно написать, значит, даже лучше, чем на планшете. Но
на четверговом семинаре люди вот включают трансляцию. Пошел.
Тоже можно.
Трансляцию можно запланировать.
Значит, давайте сначала мы решим, значит, хотим ли мы продолжать сейчас дальше до упора или значит,
Нет, сейчас страшно.
Значит, сделаем паузу. Значит, ну почему? Потому что уже все надоело. Хорошо, тогда значит, давайте сделаем паузу сейчас и значит, продолжим в субботу. Значит, теперь техническая проблема, как писать, если нет планшета. Значит, разрешим ли эту проблему? Значит, вроде значит, Никита говорит, что значит, может поделиться на время.
Хорошо.
Хорошо, тогда... значит,
Я говорю, то есть в крайнем случае можно просто...
Хорошо, тогда да, если Никита может поделиться, тогда значит, в принципе можно на этом и остановиться. Значит, ну, значит, в принципе, доска здесь, доска в 110, они тоже позволяют, имеют этот функционал, но значит, нужно уметь с ними обращаться.
То есть еще доска в 108,
значит, доска в 108, ну, все то же самое относится к ней тоже. В общем, это где-то там минут на 20, значит, освоить, значит, ключи, чтобы все работало. Вот, но, в общем, plan A, unless we come up with a better one, plan A
Во сколько?